Next, we'll see a realistic example how to use this interacting multiple model estimator in air traffic control tracking. ATC. The models used for air traffic control, civilian aircraft, have two basic modes of flight: uniform motion, straight and level flight with a constant speed and course. It's really almost constant, but close enough to that. And maneuver. And maneuvers are turning or climbing, descending. It turns out that the horizontal and vertical motion models can be assumed to be decoupled. So the design and evaluation of several estimators for the horizontal motion, which is really the more drastic one because most of the maneuvers take place in the horizontal plane, will be discussed next. The flight modes in the horizontal plane will be modeled as follows: a nearly constant velocity model for the uniform motion. Mathematically, this will be a white noise acceleration or second-order kinematic model, as discussed in 653, with a low-level process noise, and the maneuvering model. And we'll have two types of maneuvering models here. First will be the same white noise acceleration model, but with a higher level process noise, and it's important to be commensurate with the expected maneuvers, and we'll see what this means exactly with numbers. And the second one will be a nearly coordinated turn model. As you might remember, coordinated turn is motion where the speed, that's the magnitude of the velocity, stays constant, and the direction of the velocity turns at a constant rate. So the nearly constant velocity model in two Cartesian coordinates is given by the equation where xk plus 1, there are two blocks, each is a second order model, the x component, or psi in this case, and the eta component. Each will have position and velocity, so the x consists of psi dot, eta dot. They are decoupled. You can see the off-diagonal blocks are 0. The process noise in coordinate x, or psi, enters multiplied by t into psi dot by t squared over 2 into psi. Another component independent of this process noise vector would enter similarly into the eta coordinate. And what we have to do is choose the covariance q of this process noise, and it will be chosen diagonal. So we have really, in this case, full decoupling between the psi and eta coordinates. And the noise will cover small accelerations, in that case typically minor perturbations in the trajectory, turbulence, and things like that. Now, the turns really follow a pattern known as coordinated turn. Therefore, while we can use a white noise acceleration with a relatively large process noise to model, we know this is not such a good model. It is simple, but we have a better one, and we'll show its value. And this is the coordinated turn model. As indicated, it's characterized by a constant turn rate and constant speed. Remember, speed is the magnitude of the velocity. Now, actual turns are not exactly coordinated because the ground speed is really the air speed plus the wind speed, and it can be described by a coordinated turn model plus a little bit of noise representing the model error. So what we have is a nearly coordinated turn model. We still call it CT, but it's really a nearly coordinated turn model. Is going to be a non-linear one because we don't know the turn rate. It's not a known value. So we will have to augment the state vector consisting of the psi dot eta dot by omega, the unknown turn rate. So Then we'll have an equation for this nearly coordinated term model without the process noise that comes on the next page. The 5-dimensional vector is given by the previous value of this vector. You can see the coupling, and this is essentially the equation from chapter 4. And what we have is now the process noise will have 3 components. Linear process noise entering into the x or xi coordinate, second component of the linear process noise entering into the eta or y coordinate, and the third component entering into the turn rate. So the process noise has a different dimension from the one before, and so does the state. Now, we'll assume that only position measurements are available, and for simplicity here, it is assumed that position measurements are made directly in XY. Typically, radar measurements are made in polar coordinates, but they can be converted, as discussed, under pretty much all practical circumstances into Cartesian, whether you some cases you don't need debiasing, sometimes you will need debiasing. Now, how do we handle the coordinated term model, which is a nonlinear model? We have to use an EKF. There's no way to get around here. The equations for the state prediction and covariance, the only difference that is observed because of the nonlinearity will be shown below. The dynamic equation can be written compactly as new state as a 5-dimensional vector is a function of the previous 5-dimensional vector plus a gamma CT. This is a 5 by 3 matrix times a 3-dimensional process noise vector. To obtain the predicted state, we just use this nonlinear function f and use in it the function, the x hat kk. So this is the first order EKF. It turned out that in the implementation, a second order EKF showed absolutely no improvement. So the Taylor series expansion up to first order from which we start is xk plus 1 is fkx hat kk, so there's a 0th order evaluated at the previous estimate, times the Jacobian multiplying the difference between x and the previous estimate, so there's an error in the previous estimate, plus higher order terms beyond first order, plus the process noise, which is really a gamma gain, noise gain times v. The Jacobian is given here out explicitly and has to be evaluated at the latest estimate of the state. As you can see, the latest turn rate estimate appears pretty much everywhere here. We have derivatives of the omega. The last column needs some more complicated terms where we have again the previous estimate of the turn rate, omega hat k, and this is the psi dot hat, the velocity component along the psi coordinate and along the eta coordinate. They're all appearing here, so this is a little bit more complicated expression, but it's all matter of simple differentiation and algebra. Now, based on this expansion, the state prediction and state prediction covariance are, with the first order expression, first order expansion, the predicted state uses only the 0th order term, namely the nonlinear function x, f evaluated at the previous estimate, x hat kk, and the covariance for the first order expansion is the Jacobian fx evaluated at the previous estimate times the previous covariance times the Jacobian, again, transposed. So the Jacobian really plays the role of the transition matrix from the linear systems, plus the gamma Q, gamma transpose, where Q is the process noise covariance. That's a 3 by 3 matrix. Now, a very important point is, how do we start this? What is the initial estimate of the turn rate? We don't know. We started from 0. You don't know whether it will be a left turn, which would have a positive omega in the way the equations have been written. We followed here the trigonometric convention. In the navigation convention, you would have the opposite sign for the turn rates. So right turn would be a negative omega. Now, it turns out that from this initial 0 estimate, the algorithm is capable of estimating the turn rate including its sign, and consequently there is no need for left and right turn separate models as in some earlier IMM versions. It's important that at the initialization step, when the turn rate initial estimate is taken as 0, we can look at the limiting form of the Jacobian, and this is easily obtained according to this expression, because otherwise there is a singularity, so it has to be analytically evaluated, and for small values not use the general expression. Now, here we have a problem. There is an IMM in which we have two models. One has a 4-dimensional state, one has a 5-dimensional state. We had a mixing. How can we mix a 4-dimensional state with a 5-dimensional state? The answer is fairly simple. The mixing is done by augmenting the 4-dimensional state with a 5th component, which is 0. Because what is a nearly constant velocity motion? Is a coordinated turn with 0 turn rate. So it is natural that for the 4-dimensional state we append the 5th state component as 0. Then we have compatibility in the dimensions when we combine those two 5-dimensional vectors. And as far as the covariance matrix is concerned, also the 5th row and 5th column for the nearly constant velocity model in the covariance matrix will be set equal to 0. So we just augment it by a column and a row of zeros. Now we come to the design. The selection of models and parameters. We discussed how to select those models, and we have two options. The non-maneuvering is clearly a nearly constant velocity. The maneuvering is a nearly constant velocity with large noise or a coordinated turn model. So we have two options there. What are typically the requirements, or what will be the criteria to evaluate a selection and possibly refine it? The goal is to reduce as much as possible the estimation errors during the uniform motion. We want to maintain the peak estimation error during the maneuver lower than that of the unfiltered raw measurements. Historically, this has been a problem with the early filters, where when a target was maneuvering, all of a sudden the errors crept up to levels that were unacceptable, and the air traffic controllers did not want even to use any state estimator. They would prefer to use the raw data, the measurements, or as they are called, the plots. So this is the second requirement. We want to accomplish something by the measurement. So in the worst case, which a maneuver starts, typically you have a peak error until the filter catches up. You don't want to be worse than if you didn't do anything, which is what the unfiltered raw measurements will give you. Furthermore, we want to provide correct and timely indication of the flight mode, rapid detection of a maneuver. That's important. Now, how can we fulfill these requirements? We want aircraft motion models for all modes of flight. We want selection of the model parameters, such as the noise levels, to match what we mean by nearly constant velocity, the straight and level flight, or by the turns. And we want to determine the parameters of the underlying Markov chain, the transition probabilities from no maneuver to maneuver, from maneuver to no maneuver, again based on our best understanding of what is happening in this environment. Clearly, just like white noise does not perfectly model maneuvers, a Markov chain will not perfectly model the transition between maneuver and no maneuver motion modes. Nevertheless, while these are approximate, they can be and have been used very successfully in modeling things which are not exactly what we claim them to be. So they're all approximations, but they work well. So the model selection, what are the criteria of model selection? We have to consider both the quality and the complexity of the model. Typically, IMM configurations for air traffic control problems will include one nearly constant velocity model, that's for the uniform motion, and one more model for the maneuver, the nearly coordinated turn model that we have seen before. That's a typical one. Noise level selection, that's the parameters within the models. That's very important. Typically, uniform motion is better modeled with a small process noise. It may be legitimate to use a somewhat larger noise for the uniform motion to cover slow turns as well as small linear acceleration to ease the burden of modeling a broad range of maneuvers. The right choice of the noise level of the nearly coordinated turn model depends on what turn rate range is expected and how many models are to be used for the maneuvers. So the simplest case in this situation is two models with a little bit more process noise than just turbulence for the nearly constant velocity to pick up the small maneuvers, and then match the nearly coordinated turn models noises to what we believe will be the turn rates. The performance of the IMM algorithm is not very sensitive to the choice of the transition probabilities, but still it provides a certain degree of trade-off. On one hand, you have peak estimation errors at the onset of maneuver, and on the other hand, you have the maximum reduction of the estimation errors during uniform motion. The guideline for the proper choice would be to match roughly the transition probabilities with the actual mean sojourn time in each mode. It turns out that as a starting point you can calculate the mean sojourn time. We'll see the expressions of this in a moment, and use this to select those jump probabilities. We'll consider a generic ATC tracking problem. We have a sensor at the origin, provides measurements with 100 meter standard deviation in each of the two Cartesian coordinates. Actually, the location of the sensor really doesn't matter if the measurements are Cartesian. Samples are taken every 5 seconds. The aircraft starts from a distance of 25 km, 10 km at the initial time 0, flies for 125 seconds at 120 meters per second speed, that's about 240 knots, before executing a 1 degree per second coordinated turn. This amounts to about 0.2 g, that's 2 meters per second square at this speed, for 90 seconds. So it takes like a minute and a half to make a 90-degree turn. Then it flies southward for another 135 seconds, followed by now a sharper 3-degree turn. This is 0.6 g. This is typically about the maximum that under normal condition a civilian aircraft will undergo for 30 seconds. So now it takes half a minute to make a 90-degree turn. The 3 degrees per second is a typical turn rate. After that, it continues to fly westward at constant velocity, so constant speed, obviously. And we have the target trajectory shown in a figure in a moment. What is important is to see what is the maneuvering index that we have. It's about 1.5 by taking the standard deviation of the effect of the measurement noise into the position, the effect of the process noise into the position, and this is the acceleration over an interval. We see that this number 1.5 will not allow a lot of noise reduction if we design a state estimator based on the single model, which will have to be by necessity conservative. So that acceleration of 0.6 g, if we use that as a basis for the process noise standard deviation, you put it in the equation, multiply it with t squared, that's T525, you end up with a fairly large maneuvering index. So it's not a good idea to design a single model-based filter for the worst case, that's conservative, or the maximum acceleration. This is the trajectory initial, this is the slow turn 1 degree per second, this is the faster turn at 3 degree per second. In view of this, the following two models were considered and two configurations. First, a single model-based filter will be a Kalman filter, like a baseline. It was using a second-order linear kinematic model, white noise acceleration, with process noise 1 meter per second. And this is a compromise between the maximum acceleration and the constant velocity portions. So instead of going for a completely conservative, we went in this case for a compromise filter. And this is how the original ATC filters were designed, compromise between maneuver and no maneuver. Next one is IMML. It's an IMM with two linear models, both second order, white noise acceleration with low and high noise. The low noise level had a standard deviation of 0.1 meter per second square. The other one had a 2 meter per second square. And the transition probability matrix was 0.95. If it doesn't maneuver, it will continue not maneuvering. 0.05, it will start maneuvering. If it is in the middle of a maneuver with 90% will continue maneuvering, 10% will get out of maneuver. It's a little bit different than what we've seen before, and possibly this is a more realistic model. The third one is IMM-CT. That's the third filter or state estimator configuration. It's an IMM with a second-order kinematic model with low noise, again the same 0.1 meter per second square for the uniform motion, and the nearly coordinated turn with a turn rate as a state number 5, using an extended Kalman filter. Now the process noise standard deviation used in the coordinated turn model were 0.5 meter per second square. That's the linear additive noise into the psi and eta coordinates, and 0.2 degree per second square for the linear and turn portions. This is for the turn portions. So 0.5 meter per second square and 0.2 degree per second square was for the turn portions. We have a linear noise, and this is additive into the psi and eta coordinates, and into omega we had this. Just to relate it to what, if you multiply this 0.2 degree per second square by 5 seconds, you get that over 5 seconds the turn rate goes from nothing, 1 standard deviation, to 1 degree per second square. to 1 degree per second. 5 seconds times 0.1 degree per second square gives you 1 degree per second. And the mode transition probability was the same as for IMML. The initial estimates were based on 1-point initializations. We used the initial position estimate, was the first measured position, and the initial velocity and turn rate was 0. And this is because you would get, by the 2-point difference, again in this problem, a pretty large variance, so you might as well set it to 0 and give it a standard deviation equal to, say, the maximum speed in each coordinate. So the initial velocity and turn rate variances were based on the assumed maximum values. The mode set, that's which modes we use, two linear models, 2 linear modes, and 1 linear and a CT. The transition mode probability matrices, the process noise standard deviations, and the initial estimates variances are really estimate or design parameters. They should be selected based on the expected scenarios and the designer's experience. So there is a lot of engineering insight that has to be used to relate the physics of the problem with the mathematical models. And again, there is no way to perfectly match anything, but you can match it close enough so the results are pretty good.